Okay, so now I should give you this. I hope you see the sign that it works. So now back to the presentation. So what I'd like to do today is to introduce some ideas of how actually you can, I mean, of course, there's many great tools. We have seen many of them already, and we are going to see more maybe, but these tools are there for you to use for your workflows. But there's, of course, also a lot of corner cases which might not be covered by all these tools. And then I'd like to introduce you to some ideas on how you can eventually build either your own tools or how you can modify existing tools. And I will share this with matchms, which is a Python library that we built, and introduce you to this library. So I'm Florian. I work at the University of Applied Sciences in Düsseldorf, and there I'm professor for data science and machine learning. Actually, I'm sometimes also feel like I'm a starter when I come to Metabolomics meetings, but I work since a couple of years, since 5 years, with just other people on mostly cheminformatics problems and metabolomic problems. So my core interest is in applying and developing data science methods for these kind of fields. And that's also what we did with matchms. So before we get started, this works. So I'd like to ask a question. Who of you knows how to program? Maybe you can raise a hand. That's a few. So I was expecting this actually. So I'll ask the same question again and say, like, who has some programming experience? Okay, that's much better actually. To assure, I didn't expect full-scale programmers to come here, so you don't have to have programming skills for this session. So don't worry. This is just for me to know roughly what kind of speed we're going to do, and we can also interact. So feel free, especially during this live coding session, to interact, to raise your hand, to pose questions. There are no stupid questions, so just really try to force me to go your speed and not try to follow my speed. So that's, I think that's it. So the same question again now about Python. Who has some work with Python before? Okay, it's quite a few people actually. Again, this is not necessary for the session. It's just that matchms happens to be a Python library, so we're going to work with Python. The question maybe I also like to ask is, okay, why do you need to program, right? So why should you? And there's a couple of reasons. I'll only name a few of them. So the number one reason for me is, I think, the following. I consider programming as a door opener, right? So programming is a door opener, including doors that your PIs maybe do not want you to go into. That means kind of if you happen to learn, I don't know, I guess many of you are PhD students, postdocs, or math students, and if you happen to somehow squeeze in the time to learn a programming language during your PhD or postdoc or whatever time it is, if it's any programming language, doesn't matter if it's Python or R or Java or C#, this will open doors for you, including doors outside academia, right? So I'm not giving career advice here, because I assume that many of you will stay hopefully in academia, but still I think this is something that I learned that is quite hopeful. It's broadening your skills to quite an extent, so it's worth spending some time on it. But of course today I'd like to give mainly a career advice of how to leave academia, but more of how you could do great things in academia. So, and this includes the same saying, you can open a lot of doors by knowing how to script, how to program. And this means you don't have to be a professional full-scale software developer to do this. If you already know a bit your way around some of the tools, and it doesn't matter if it's R or Python or Java, this will allow you to do things that other people in the field might not do, and it will allow you to develop your own ideas to an extent that you cannot do without programming. So that's the main motivation. There's other reasons for this, but I think this is by far the number one reason. Another thing that I should remind everybody is kind of don't trust people that tell you that go to you and tell you Python is easy. That's not. So it's like saying, I don't know, English is easy to learn or something. There's always these sayings, and I don't know if it's true. Maybe with respect to Danish, I heard, but I'm not going into this discussion today. It's more that Python is not easy. Like any full-scale programming language, it has its own difficulties. It's an accessible, approachable language, I would say. So it's a good language if you want to start, especially if you like working with data. But don't be frustrated because I mean, don't think you're not good enough as a programmer, because it's quite normal to have a hard way to go into a new language that you learn. One thing I'd like to mention at the beginning is a bit like from what angle I actually start to develop tools. And there's a couple of things like two I like to mention. And one big interest in this field of metabolomics here is the unknown unknowns. I think most of you have heard of this dark matter thing. So right, so this, and we have had this topic in different wordings many times this week. There's so much data that we have a hard time interpreting. And that's for me the unknown unknowns. And I think it's really worth developing new methods to go after this, because everybody here kind of has this sensation of this feeling that there is so much information there that we're just not using yet, or not the right way. And that's why we, all of these people that you've heard the last days, are using these tools to shed light on all these compounds that we have no idea about what they are. So this is the scientific motivation behind this mainly, but there's another one, and that's not the unknown unknowns, but I can say it's the unclear unclears. I don't know if this exists as an English word, but no, it exists. So what it is now that the same happens a bit for the method side, right? So we not only don't know what we don't know about our data sometimes, but we also don't know what we don't know about our methods, or sometimes it's a bit different, but we don't know exactly what we really want, and so it's hard to judge what the method should do. And I will come with an example in a second. So one example is the term that you've heard many times here, spectrum similarity. I also use the term many times, spectrum similarity. We use it in matchms, it's similarity scores. But actually it can be quite confusing, or you have to define it further. So because you have to ask yourself the question often, if you use these scores, what do you actually want? And what do you actually mean with similarity? So there can be different things. So you might mean you want to have two spectra that are nearly looking identical, right? So you have the same MZ positions, the same intensities. That's what the cosine score would do, maybe. But it can also be, and we have seen many examples of this, that maybe that's not exactly what you're looking for. Maybe you don't care if the spectra look really similar, but you care about the chemistry behind this. And then you could say, like, okay, maybe you are more interested in defining similar peak patterns. It would be something maybe in the direction of the modified cosine score, or into MassQL, what Ming presented yesterday. Or maybe you straight away, actually, you don't care about the spectra at all, and you just want to know what similar chemistry happens. And asking this question yourself, or answering this question, makes a lot of difference in what kind of methods and what kind of scores you develop and you pick. There's another question you should ask yourself, I think, if you use these spectral similarities, and that's what is most important to you in technical terms. And that is, you could say, like, what's your number one priority? Is this to find all the similar compounds, or no, sorry, is this to find similar compounds with high certainty, or is this to find most of the similar compounds? And typically these two things, you cannot have both of them. Even if you use very sophisticated tools like Sirius or others, you somehow, at some point, you have to make a choice, right? So in Sirius, you would do this with a certainty score maybe, but there is a choice you have to make between what is your core interest. Do you want to have a lot of data with probably more faulty data in there, or do you want to only cherry pick the best examples? And a less frequent use case, but you could also ask the same question the other way around, is kind of, do you want to identify dissimilar compounds? So usually in most of the cases until now, I think in really all cases, we focused on similar spectra, but you could also ask the same questions the other way around, like, do you care about finding dissimilar compounds? For example, you could say a use case I can make up is you want to clean up a library, right? So you want to find matches that shouldn't be there. And so my question to you, to get into, we are in the gymnastics hall, so we get into some brain gymnastics, is which of these four tasks can be done using the cosine score? Give me a second to think, and then I will expect to wait to answer for that. Anybody have an answer on this? Or it can be a guess. Guesses are fine. You have a 1 to 4 chance at least. And then we can still discuss it in the answers, right? Anybody, any feeling of what do you do to bet your money on? Yes. Yeah, so you go for the first one, basically, and there anyone has an opposite opinion you want to defend? I think it's up to discussion, right? So there's not a final answer to this, but I would also go for the first one mostly. And the thing is, kind of the cosine score really looks at nearly identical spectra. And if you have chosen your parameters right, or like your tolerance, and if the data is clean enough, then it's not, we can discuss if this is the optimal score or something for this, but at least I think it's made mostly for this. What you certainly cannot do with a cosine score is the second thing. So if you want to find, because I'm not looking at identical compounds or identical spectra here, I'm looking at similar compounds, and this is something the cosine score cannot do. So, and similar also in the cosine score, or in modified cosine better maybe, but in the cosine score, it would really be like nearly identical compounds. So for some things you can use this score, for other you can't. And one score we're going to use that I'm proposing today as a totally different route is MS2 deep score. We will see later, and this is more focused on actually the other two points. So we had spectral similarity, and actually that it's not so simple as it sometimes seems. And the same is true with molecular networking, I think, because we did it yesterday, or you did it yesterday, and it's a really nice tool. So I don't want to discourage you to use it. It's a great tool, and it's a really great way to explore complex data that you have here. But there's also a lot of questions behind that sometimes go unanswered, and that is actually, what do you consider a network? And this is maybe also triggered because I'm not coming from the field, but I'm more coming from data science, where networks and graph theory also have different connotations sometimes. But one question is really essential, of course, is, and that we touched yesterday, or you touched yesterday, is like, what should be a connection in the network? Because I mean, typically networks, the classical case of a network comes from totally different fields. It comes from people being connected or not, or you have a social network graph, and then it's really clear what a connection is. But here we are talking about, okay, why should two spectra be connected? And they can be connected because they were in the same sample, but that's usually not what you want. You typically do what you did yesterday, you connect them by a score. And so you use a score, which brings us back to the last slide. Okay, what is the score and what do you want as a score? And what is the threshold as a score? But we also touched some of these points yesterday, but there's many other ways. So it's not as simple as that. You have to choose a score, but you also have to choose, okay, how do you go further from that? There's a lot of scripts out there where people do tweaking and tuning of these networks by removing edges, adding edges, or edges of connections. I don't know if I'm confusing here. So, but to add connections in this network, you can do editing things. You can add multiple scores, which we've yesterday seen with the motifs, for example. So there's many choices, and it really depends on what you expect the network to be. And this is related to the question of what do you really look for? Because sometimes it's not so clear if you actually really are looking for a network itself, or if you just use a network as a vehicle to find out more about your data. Of course, a network is really attractive because it is looking nice. I think most people have the same idea about networks. So they make nice plots. They are fun to play with. So that's fair enough, and it's good to go. But there's some hidden questions which you can answer with networks, but not only with networks. So one question that I see often, for example, is actually that people are looking into clustering. So actually what you want to do maybe sometimes is to formulate molecular families. And in the language of graphs and networks, people would speak of communities, which you can define as a cluster as well. But what I'm trying to say here is that maybe a network is not always the ideal way to do. If you really just want to have similar compounds clustered, you can go with a network, but it's not often the ideal way, because networks, for example, have this difficulty in everybody that has played with thresholds knows this, that they tend to have too many edges, especially if you get to large data sets. And so it's not so simple to really identify small subunits that are separated. So that's why many people do tweaking by removing edges to get these separate clusters. This is just to say, like, okay, you can use a network for many things, but there's many other techniques out there in the world of data science for things like clustering, for example. Which now brings us finally to the tool I'd like to present, and that's matchms. So matchms is a fairly new Python tool, fairly new because it was released first in 2020, and it's under constant development, I would say. So it's a moving target, you could also say, but I would say it's something progressing and developing. And this is a Python library with many different goals, or several goals in mind. I will go into this in a second. But first, to get started, so there's different ways how you can follow this session now from the next 2 hours or 2.5 hours. And this is, you can of course listen and watch, which I would not recommend so much because I think that's the most boring way to follow this. The better way is to code along. So really to try scripting and coding yourself. And there's 2 ways. You can do this with the Jupyter notebooks that we just nicely got introduced this morning. And that is totally feasible, and this means you can run it on your own machine. But I would warn you that since there are so many participants and have so little time, that this assumes that you know your way around in these notebooks a bit. So if you don't feel confident enough with your own Python environments and notebooks, I would really recommend that you go for the Google Colab version. I personally nearly never work with Google Colab, only for these settings like here, where you have many participants that need to start or run a notebook. But for this purpose, it should work fine. So I recommend most people that don't feel confident for the second step to really start with the Google Colab. And it gives the same result. Ideally, it should give the same result. So there's no benefit over running it on your own computer. It's more if you really are already into this Jupyter Notebooks and Python environments, feel free to do it wherever you like. A few words of warning. I'll come to, because we had some nice software like NZMine and Sirius and NTMSS. So let's compare it with our user interface, which is this. Sorry, it's not always as ugly as this, but this is our user experience. And you can see that it's not meant as a quick introductory, very accessible tool, which has some reasons. And you can also see this way. This is how I see our user interface. It's like this. So you actually do things with your hands. We have to type fast and weird phrases, and hopefully the computer will understand what we mean. Often it will not. We'll see that in a second. And so this is what we're going to do. We're going to run through some notebooks, but because this typing is so difficult sometimes, most of the parts are already in place. So the notebooks is made, but it's pre-made, so there's only a few missing pieces, which will help us to really go through a lot of code, not a lot of code, but through a whole process in the next session. Why do we prefer this over a proper web-based interface or something like this? The reason is simple. That's not really the focus of our project so far. So matchms was built with a really small team. So currently we are usually less than a handful of developers working on it at the same time. So now I think currently it's like 3 active people, which includes me. And the focus of this tool is really more on the development of new methods. And so matchms is not, the idea is not to have the biggest, greatest, easiest ever user experience, but it's more meant as, or it has 2 central goals in mind. There's several others, but these are the 2 main ones I would like to mention. And one is kind of to really provide performance spectrum handling and quick comparison of spectra. And the second thing is more general. I'd like to have it as a robust, well-maintained platform for us and for other people to develop their own Python libraries and tools. So how does it work? Before we start, a few ideas about some key concepts in this software matchms, in this library. The core element of matchms is a spectrum, and a spectrum is, I think most of what spectrum is here, but in the coding world, this is a certain object, a unit in this program that can do certain things. And typically, what we do is we import or export our data from some files. Here, and in many other cases, we will use data that comes straight out of NZMine. We can import it, we will see that in a second, or in a minute, and then we have our spectrum objects, and these have certain properties. They have fragments, which means they contain peak positions and intensity. So this is really the fragmentation patterns, the MS2 data, and they have the metadata, which is kind of all things that come with these spectra or that we later add to these spectra. Could be annotations, could be precursor mass, could be things like scan number or feature ID. All these things go into the metadata. Of course, not everybody uses NZMine to its full capacity, so we often have to deal with data that is not finished when we load it from some data set. So we provide a lot of functions in the matchms to process these spectra further, and then we have a spectrum processor for this that can handle many different filtering steps. The main thing that it does is kind of to make sure that they are executed in more or less the right order. And then we can create a new spectrum from an imported spectrum, which might have different fragments, different metadata. Where, for example, you could think of things like you want to remove small peaks, or you want to remove peaks outside of a certain window, or you want to add or change or edit metadata. Once you have the spectrum in the form that you like to have it, the key step that we typically work for in matchms is to really compare spectra. And this is with a similarity computation. And What this gives you is scores. Of course, it gives you scores, right? But here it's a scores object, and the scores object means this is a unit in the program of matchms that has a lot of properties and methods to it, or functions that you can use. And we can, with the scores, we can later create networks or do other things that I'm going to show you. One thing I want to say about scores is that scores is not what you might immediately think of. It's not just a simple table of what the scores were between spectrum 1 and 2, because what we've seen over the years is kind of that we actually want to go, or we want to be performant enough to also compare many thousands or 10,000s of spectra. And that creates a big problem, namely that you have far more scores than you're interested in. So what scores is currently in matchms, it's a so-called sparse array. So it's what we introduce here is kind of that we typically don't, I mean, you can store every score, but I will show you some ways around this. So typically you will see that most things we're not interested in. If you think of, for example, the data we have today is about 6,000 spectra in the data. If you compare them all to each other, you get 6,000 by 6,000 scores, and most of them will be really irrelevant for us. So typically what we do inside is kind of to really also be scalable, is we define certain rules, and then we keep the scores that we actually are interested in. And we can text them. So it can be that you are interested in multiple scores. For example, it could be that first you want to see if you have a precursor mass match, and then you want to compute the cosine score. And in the end, everything can be combined into one big workflow. And that is where finally it gets a bit simpler in the end. If you have to find your workflow, you can export it as a YAML file, which in practice should make it for yourself very reproducible, because you can simply import the YAML file, change something in the YAML file, and run the full workflow again. With this, I'd like to switch to Google Colab. And let's try to open this up. So I hope that you downloaded the folder, or maybe you uploaded it to your own drive. Let me just try it myself here. So there's different notebooks in there. In this Google folder, they have there's a folder that says notebooks. There's also one that says notebook solutions. I will keep this for later. So this is just if you fall behind or if you want to see things later on. The purpose of today is to really go through some notebooks which are not complete yet. So one is, when we start, is kind of the summer school matching. So I'll show you how. This, I think it's different in your drive, but this is. As summer school matching as live coding. I will try to move it to the screen. And the resolution change. And now the screen is feeling some pixels. So the notebook, this is the name of the notebook, Summer School Matching as Live Coding. And if you open it in Google Colab, it should look like this. I'll wait a bit for everybody to open this kind of notebook, and please raise hands if you cannot find it, if you cannot open it, or you have any other things popping up. Yeah, sometimes there's difficulties to open. So there's different routes how you can go there. So this I opened directly from my own Google Drive with a double click, but it's not always work. Sometimes you have to open Google Colab first and then import the notebooks. We tried some things yesterday, so it looks like it's not on every computer the same, but so please raise your hand if you have trouble opening or finding it. Yeah, so there's different ways how you can handle these notebooks. So so there's also a way to import it here, right? So you can say you can go to. Oh, sorry, I have the German way, which is not so good. So if you go to File, you can also open notebooks. Right? So you can open a notebook, or you can upload a notebook. So there's different ways to open it. If you don't have it on your drive yet, you can also go to Upload Notebook and work this way. If you have copied it to your own Google Drive, I think it should work from there as well. So you can open the notebook and search. Okay, so I mean, uploading is really asking you to point to a file in your folder, which will then be uploaded and you can start it. If you go to open, then it will show you some notebooks that you have seen before, which of course in your case might be none. But you can go to your Google Drive, and then you can inspect your Google Drive and go into the right folders, and hopefully you'll find it there. Then there's still the option of upload. This really means you can, okay, this is German again, it's stupid, but it's whatever your language you have. But this is kind of, you can upload the files. It's easy, it's just a notebook file. Just to get it on here, who of you has this notebook in front of you now? Okay, that's still missing, I think. Yeah, so I think there's two very steps I think today. Like, one is to get this notebook running, and the second thing is we will later see is to import your own files. Okay? If we are beyond this point, then we see. So as I said, sometimes it works with just going to your own, copying it to your own Google Drive and double clicking on it. That not always works. If not, you have to open Colab yourself, and you have to just go to the Colab. You can just search it, go to Google Colab, and then import it via file. And via opening it. So for the ones who have it open already, there's a few things just that I can tell as introduction to these notebooks. They work, of course, on Google Service. They have a certain Python version, certain libraries pre-installed. So you have less control over what's in there or on there than if you would not run your notebook on your local computer. But for most things, especially for quick trials, this should work. And for us, hopefully it will work. But of course, matchms is growing, but it's not growing fast enough so that Google would automatically install it for us. So you have to install it yourself. And this is the first code cell that we have here. The principle of executing code in this Google Colab things is the same as in what we just seen before in the Jupyter notebooks, right? So you can have markdown cells. So this is if you double click on this, you will see how this is actually looking like in terms of code. Let's say this is markdown, and if you then hit Shift Enter, it will execute, which in this piece of the text cell just means it will render it as a text. So this, behind this is markdown, and as was said before, you can use it to do any kind of documentation to your own notebooks, right? So you could add text, tables, formulas, as we heard, and many other things. And what you can do is typically you can add cells. So you can say insert, and then you have a text cell, or you can have a code cell. And this is already a prefabricated code cell, but you could add any other code cell you like. So you can say insert code cell, you typically get an empty cell, and you can do whatever you want. You can do these classical things in the programming world and say how it is, which is very spectacular as a result. It will print well. And the way you type it as Python code, and then you click Shift Enter and you run it. And the reason this takes so long is not because it's such a complicated command, but because that's the first thing I execute something in this notebook, and it has to initiate the notebook. So in these cells, you can really enter every code that you like, which, as long as it's Python code, it's properly executable, will run in this notebook. So you can, you can also click on Run here. The other thing is you hit Shift Enter to run these cells. And something that is weird in these notebooks, and I should say as a warning, especially for people that come from programming, hate about these notebooks, is that there's no proper order for execution of the code, right? So I can execute this code, I can go up and execute this code, I can go down and execute this code again, I can change it, go back up, and this means it can become quite messy. You will see this if you work on these notebooks. But the nice thing is that it's a very small barrier towards executing Python code yourself. And so if you have this notebook running, the first thing you really need to execute is this command. This is a bit weird command, I have to mention. It's not Python code. It has this sign before, and this sign says it's actually a terminal command. So it actually will execute not Python code, but it will execute this, in this case, a pip install. This means we want to install a library. And what we do then, this will, on the server, you'll see it will download the package matchms, so the library that we built, but it will download much more. It will download our library, but it will also download all the libraries that our library wants to have. And this might take some time because it will download many things. It might look a bit frustrating, but it's scary that it's doing so many things. But this is essentially how you have to set up your notebook. If you would work on your own Jupyter notebook locally, this is not a necessary step, because usually you would create a so-called environment. Right? So you would create a small programming environment where you install all the libraries that you want to have. So this is one you can ignore. Don't worry about this. This will come. The main message is that it successfully installed all the stuff. So this is something that also was mentioned in the talk before. This can be annoying if you install a lot of packages, because if you restart this notebook tomorrow, you have to do the same thing again. And this is now fine because it didn't take so long, but if you work more with notebooks, you will see that at some point you will call it as frustrating, and you will switch to Jupyter notebooks. So now that we have this installed, that's actually, we're pretty much done with the code side, or with getting the code to run, because now we can really use everything that's in matchms and run this code. Yes, yes. No, you don't. So it says you need to, but I think that this is more for the pip update, so you don't have to. So this will run like this. So you don't have to do anything. So just you get this warning, just now. There will be many other warnings you would have to. Yeah, including usually we just ignore warnings, so now we include error. No, but this is, so what this says is, and that's especially in Python, but also some other languages, is you have many dependencies. And dependencies, what does it mean? Dependencies mean there's so there's people like me and many others that develop Python libraries. So we provide Python code that you can simply with one click import. But then, of course, I'm not doing everything from scratch, right? So if I have in our library matchms, we use tools that other people built. And these tools might use other tools that other people built. And so you can quickly imagine that there's a whole tree of dependencies. Like you use code from other people, and that's also how it's supposed to be. But of course, then comes this thing of versioning. So we change our code occasionally, we break our code, and this happens to other people too. So the complicated thing about this is that's usually not our concern as long as it works, is that you have to get these libraries to be compatible still. And what this says actually is that it cannot assure that this is the case. Because so it cannot resolve all the issues. So apparently there's some versions that, for example, you might have, say, matchms uses a library ABC that must be in a version higher than 4, and then we import a library that needs ABC in a version lower than 4, and we have a conflict. And these things happen, and they sometimes pop up here. If you were unlucky, they will also make your code not run, but here we are safe.
So maybe to ask, so who is up into this stage? Hands up.
Oh, that's very good.
That's an unsurprisingly good score.
Now we have done the session 100 of times, and yeah, so that's.
So for those of you that are not yet there, please, I think by now it's better to watch with your neighbor, because there should be at least one neighbor judging from the hands for which it works, yeah. And then maybe in the break we can see why it still doesn't work. Okay.
Yeah, that's a very good remark. Thanks. So. To be honest, I didn't say this to discourage people. That's the first time that we try this in live coding session, so because it works. So I will guide you through the code. So as I said, so it's not about typing every line of code because I assume that you can read text and type text. It's also not about just executing code cells. So we have to find the right balance here. So if I would provide, that was also mentioned before, if I provide a notebook to somebody that doesn't know anything, usually this person can still execute these notebooks, because what you would do is just either you find the menu button that says execute all, or you just don't worry and you go through all the code cells and hit shift enter, shift enter, shift enter, shift enter, and then you ideally get the plots in the end and say, yeah, I got it to work, I can code. Experience has it that typically this means you will not understand what you just did. We made a joke yesterday, so I just as a warning, we didn't do this, don't worry, that we could also, because this is a Jupyter notebook, and sorry, I should do this later because it's not yet connected to the Google Drive, eventually it will be. You could also add a code cell, say, delete your Google Drive. This is not in there, but be careful, read all cells before you execute them. That's what I want. So read all cells, but of course we will have some code cells that are not working. So you cannot go through this notebook and just click shift enter. It will not work because we don't want you to do this. But for some cells we want to, and I will quickly explain what all these cells do. But please, if you want to know more about this, raise your hand, ask a question, and then we can explain exactly what we do there. So the first cell is we import libraries. So now we installed the library, but it's not yet imported. So installed means kind of on the back of this, on the server side, they now installed for us matchms and all the packages that matchms needs, but we don't have matchms in this notebook yet. For this, we need to import it. With Python, you simply type import and the name of the package. But yeah, now that I said it's not that simple because you can import it in different ways. So I don't want to go into too much details, but what we do here essentially is we import a few things from matchms. So this is score calculation and the loading of MGS files. There's many other things in matchms, but here I just start with these two. And the things on top, these are just libraries that we're going to need for file handling and fault integration. So if you do the same here, this might take a bit of time because it will import the libraries and also the libraries that these libraries need, if that's for these functions required. If you get errors, let's say that you don't get this green check mark and something pops up, and also let us know. So after these imports, what we're going to do next is we want to import our data. And this is where now it gets a bit more difficult because, or at least I'm curious to see how it goes, because we need to get our data onto this notebook. This notebook is running in the cloud, so it doesn't know anything about what files we have. So there's multiple ways of how we can actually get the data in this notebook. If you would run it locally in Jupyter Notebook, you have to provide the path to where it is on your computer, and you can import the file. Here we don't have the file yet, and there's different ways how you can add the data that you maybe downloaded to your notebook. You see here on the left side, there's files. If you click on this, it should like open up, and you see several options of how you can add data to this notebook, which means you can upload data to the notebook. And luckily today we don't need huge files, or not so huge. So there's several ways that we can go. I start with a backup option, which you're not supposed to do, or which is not plan A. So you can simply upload every file that you need, and we're only going to need 3 files, I think. But one of them is a trained model later on, so it's a bit slower to upload, but you can. So if you just click on this, you don't do this now, but if you would click on this, you can upload 1 file at a time. There's another way to do it, and this is in this code, so that it will also appear. So if you click on this, this means bound drive. So this means it will connect your own Google Drive to this notebook. If you click on this, it will actually produce code. It will actually produce this code cell, and simply execute it here, and then there should be a pop-up saying, "Yes, I wanted to connect to my Google Drive." This is where you start to have some trust in what I'm doing. Is you have to connect with your own account. I mean, I'm not seeing your account, but it's meaning that essentially this thing now has access to your Google Drive. So I hope that you don't have too sensitive data on there anyway, but let's say that's a bit scary sometimes. So you can, if you're too scared, just do the upload. But this is a convenient way, so I'm doing this convenient way today. What this means kind of is it takes a bit of time, but then it can access your Google Drive as if it would be a drive on your computer. And when you've done this, then it depends on where you move the files. So I think in the instruction we said you should ideally download the folder and upload it to your Google Drive. This only works if you have done so. And if you upload it to your Google Drive, you should check where it is on the Google Drive. What I have here is also not correct, not even for me, I believe. But I don't know. I think it is. I hope it's here. So because what you have to change is this address here. So this is my Google Drive. It says my drive, and I mean it says my drive for everybody, but it's your drive now. And then it's whatever folder you have where you copied all the data, or all the files. In my case, it should be this, and this is what I call here. I call it pass root. This is what I do for people not into programming. This is just setting a variable. So I save this name under this. I think it's under this name. So it's now called pass root. And what I do in the next line, without going into too much detail, is kind of I want to specify the file I need to import. And so what this says is I combine my folder name with another subfolder name with the actual file name. And today, I mean later on, I hope that we do this with data related to a group. But here we start to use the example data. And this is the data that was produced by Mine. And if I'm lucky, this will work. For many of you, it probably won't, because you might have your file incorrect. So if you have a folder that is, I don't know, if I do use wrong syntax, let's say if I have a subfolder, maybe your folder is different. And if you do this, then you should get an error. So several of you will find this file not found, file in this file not found areas. And says this folder doesn't exist, or this file doesn't exist. If you have this error, then just try to look up on your Google folder where exactly do you actually really store my data. And then we correct it again. So this is executed without any error, and you're safe. See some people that apparently didn't get it to work. Cheering. That's good. There's a hand. Yeah, if it's on the Google Drive, that's fine as well. So you can, I mean, of course, you can upload it to Google Drive, but that's not right. So you can also do this thing, and that says, then you can really click in your files. If you have it on your local folder, you click on any file and you say open. I mean, the thing is, it's quite insisting on German here, but even if I change it to English many times. anyway, it should say that, yeah, it's just an open menu that comes. So again, so this is this button here. So if you go to files and you go to this symbol here, this means you can upload a file from your hard disk. And in this case, and then you should pick, what you then should pick is this file, only this file, example, IMGS. You can find it either in the data that you downloaded from the link that I provided yesterday, or you can also find it in the GitHub actually. So this is the same file that we use as the output from NZMine for the example data set. And this will be quick because this is a small file, so Google will upload it very quickly. If you upload it, you should see a progress bar where it's kind of slowly uploading. Now, actually, one thing I think that I should mention is if you upload this, maybe I should also do it. My folder structure, which is horrible, but you have it. Okay, I'll show you all my crap folders. Projects, underscore, and there should be the data somewhere. So if you click on this example, so if you click on open, then warning, yeah, okay. Yeah. So it warns you if you import it from somewhere else, it warns you that this will be deleted afterwards, right? So, or not deleted, it's, I think because it's just, this is not an upload to your Google Drive then, it's an upload to this instance that is running. And as we heard before, if you don't use them for 90 minutes or if you run them for more than 12 hours, this will shut down and you have to restart it, which includes that everything you did is lost. I mean, you can download things, of course, but it's not safe there forever. Yeah, but you can upload it, and then it's kind of it's in there. So I think it's uploaded here. It's surprisingly slow. Maybe that's because many people are doing that. So what this tells you on the bottom side is kind of this is the space on the virtual disk that we have there. So and then it's uploading the files. ES one. Usually that should go fast because it really small files. But I hope that you get it on faster than this. The only thing that you have to change if you do this actually is kind of that that this command will probably not work. So if you did it, I will show you a different piece of code. Actually, you can move these cells, by the way, if you click on these arrows. But because what I did here is, without telling you, is not only define the file name of the path, but I also just straight away imported data. So this is, I called it Spectra, and then I imported with the matchms function that we imported above, so it's loaded from NTF, then we have the file. But of course, if your file is not this file here, but it's the file that you just uploaded, then you have to add a different command. And I'm just writing the same line for the people. This is only for the people that do not have it mounted on their Google Drive. You need to import from, and then I think now it's done. And here you have to copy and paste or type the file, right? Example, MGF. Because now that's a different route to go to the data. So now it's really imported locally. It knows that this is the file. You can see it in there. And then you have to import it, or you can import it directly into offline. You can import it straight away from this. Yes? So the Spectra you mean, or?
Yeah, you have environment and you see what you are.
No, here you can't actually. So so it depends on where you work with. In these notebooks, you can't. There is certain programming environments, for example, in Anaconda the Spider, for example, and you have Variable Explorer and other software you have it too. So we have now Spectra, but we don't know what it is until now. We'll see what it is, but that's what we meant, right? So you have Spectra, but where is it, right? So where is it? What is it? We'll look at Spectra in a second. I first want to see if everybody can get it in. Who has not yet, or where did we work to import the data? That's something we can go really long. Okay, so I assume it. Otherwise, please raise your hand. So ideally, one of these lines should actually be fine, and then you have spectra. But as was just mentioned, we don't see them anymore, right? So they don't pop up. There's no visuals. There's nothing. So this, if you scroll down, this is what we have next. So what do we get from this? And this is, so you can execute these code cells. So this is just regular Python code. It will give you some information about what we actually got. This is not usually what I would do in a notebook, of course, because I know what it gives me. But this is to show you a bit how or what kind of data or data formats we actually have here. So data spectrum is, or spectra here is, that's the import from the NGF file. What this does from matchms is kind of, it really reads the full file, and it creates separate spectra or spectrums for all the spectra in there. And it creates a list. And this list has a length that you can ask for with this. So this means essentially that we have a list with 6,122 elements. I think if you have the same number, ideally. If you do not, then let me know. It'd be surprising. And then you can ask, okay, what is it actually? In Python, if you want to ask something about what are you, you say type. What type are you, right? So type spectrum. And it just says, okay, I'm a list. That's not really real, but that's the basic information. I can tell you a bit more what it is, and this is kind of, a list is a collection or an array, and it means kind of it has just a series of different, so all the spectrums that we have in our data are now here. And you can access individual ones by saying spectrum or spectra, and then you enter a number. You can say the first one is 0, so in programming you start to count from 0. And this is also not extremely informative. You just learned that this is a matchms spectrum. And this is what I meant. So this is the central unit in matchms you should get familiar with if you start to build software on top of matchms. So every spectrum is now stored as one of these spectrum things. Okay. Can you see? Should I make it bigger? And this is, so you can say like whatever spectrum you like, and it doesn't give you the information you maybe are interested in, because it just tells you I'm a spectrum and I'm in a certain place in your memory. That's all. So far, that's not really informative. So if you have this, let's get a bit familiar with the spectrum itself. In this programming framework of matchms, the spectrum is really our central building block. So everything we do with these elements, because they have certain properties that we use in our filter functions, we use when we compare spectra. And if you use this more, you should get a bit familiar with this thing. And so we do a mini exercise on this in a second. The spectrum is having a lot of pieces, or not a lot of, it has these two pieces that I mentioned. It has peaks and it has metadata. And so you would say, okay, if I want to get the metadata, you just have to say point metadata and execute it. If you want to get the peaks, you type peaks. If you want to get something else, you can use all the commands that are here. These are not all the commands that we have, but these are just some of them. And so now I would like to give you a couple of minutes to go through some mini exercises. So use these things that you see above, and of course, I think you have a hint. No, I think in your code maybe there's a hint. So if I say spectrum, this means you have a single like with single spectrum, you need one spectrum at a time, and then you can add these dot peaks mz, dot peaks intensities, dot metadata, and you will see that you can read then some of the information that is stored in this spectrum. Just try it out. You cannot break anything, or I'll give you credit if you can actually. So let's get extra points on your ECTS. So you notice, right? So you just type something, if you type something wrong, type something in, it doesn't matter. You have some code cells here. You can add always more code cells by this insert or by a plus button. Like if you go here, you can say plus code or plus text. And just try to answer these questions. And there are like, okay, how many fragments has the first spectrum? The second question is, what is the highest fragment MZ ratio? And then there's also methods that are called, there's get and set. Actually, there's an error in the markdown. So this should not be get. I can correct it here, which doesn't help you because it's only correcting my version. Anyway, This should be spectrum set. Small, but meaningful. Let's see. So you have, so this is the methods above are just to inspect things, and here you can, if you want to access individual metadata fields in the spectrum, you can get this spectrum get charge, and if there is a charge saved, you will get the value for the charge. If you want to set a charge, you would say like set charge, and then you say to what value you want to set it. Maybe not a meaningful operation here, but you can set it to an try to use these commands to go through these questions and to get a bit familiar with how these objects work. And feel free to ask questions if you don't know what to do, if you get errors that you don't understand, or any other problem you face. Yeah. 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 Yeah, that's a good question, actually. So I mean, if there's nobody in front of you that tells you what the options are, how do you get the options, right? That's a good question. I should have got some links for this. Usually, so if you say you have spectra, I don't know, I want to look at spectrum 178, and you start with a dot. I should try to correct, otherwise it will not understand. It's a bit reluctant. So you can, after the dot, you can click on the tab. And sometimes it will suggest you things, but the problem with these notebooks is that often it doesn't. For example, here it doesn't. You later see some cases where it works. In a proper programming environment, you would usually get hints. You would have hints because it will read what this is, and it will give you hints on what you can do. Here you can't. So the only way you can do is actually you go to the documentation of the software itself. And then there's a section for every of these elements. There's a section for a spectrum. So I will open this. I think. A little time to open this now. Let's see. I'll open the second window too. Yeah. So on matchms there's a documentation, and this documentation this will tell you the options that you have. Which brings us back to the cumbersome interface, but so on this, like if you click on the matchms, for example, you go to GitHub and you click the documentation, you see that there is these elements, and you can, for example, go to the spectrum, and then this will already list you the options that you have. So you can do things like okay, metadata. Some of them are not important for you, but you can create hashes, you can set things, you can plot things, and if you click on it, it should reveal a bit of how this is done. So if you're lucky, then we try to provide as much as possible code examples. So then you get some example of how this is actually used, for example, and how you can get things like here, for example, these intensities, and then this will give you something. Yeah, it's a trial.
That actually was
So to give some hint on the way, since some questions were on what is the first spectrum, so how can you get the first spectrum in your data now? Can anybody else know? Somebody know how can you get the first spectrum that we have loaded in? Yes.
Spectra square bracket 0.
Yes. So you can. They're all numbered, and which is not the most convenient, but this is just a list. And if you have spectra 0, this is actually the first spectrum that you will get. This will not reveal anything that can answer any of these questions. But of course, with the method that you see above, you should be able to see, for example, this one, how many fragments or peaks does this first spectrum have? Yeah, then it's, so you have different options. And you go with, I guess you go with peaks or something. Yes. So you have the peaks. The peaks itself will not reveal much, but you can ask for the length of this spectrum. And then this will give you the number of peaks. That's not the only way to answer the question, right? So you have, you can do this. Or actually, by the way, if you add a hashtag, it's not because it's important, it's because we want to not run this code. So this is just to show you there's a different option. You could also say spectra 0, and please give me, which is related to the second one. How would you get the highest fragment? Or how would you get the, the MZ values? Anything else there? Yeah, you add .mz. So this is great. Okay, now finally you saw that it sometimes works. It gives you hints. And now you know that it has a sync intensity and that, and you can add in that. And then you will see that these are, for this spectrum, these are the values for this particular spectrum. And of course, you have Python functions for getting you the maximum and so on, but this is not what I was after. I was just after to give you some idea of how you actually interact with these things. Did you set a note to the supervisor? Yeah. Did it work? Okay, so I'll let you deal with that. Okay, so one general remark is, so if you ran these methods above, so one thing that is of course helpful to get a bit of an idea of what you actually have in front of you is to simply say .metadata and run this, and this will give you the metadata that has stored for this particular spectrum. This is not exactly, it doesn't have to be what's in your MGF file. So this can be of course different because even when importing, things are harmonized within matchms2 style of what matchms calls these fields. But this is, so far we didn't do anything fancy to the spectrum, so this is the information that came with the MGF file. So in this particular case, you see that it has certain headnots, it created the first embed from this, it has a charge, attention time was saved, the scan number, and the feature ID, which is the same. So these information are in this one particular spectrum. If you would like to add something, you can always do this with the setting, right? So if you say spectra 0, in this case we just have it with the first one, you can say set, and then whatever you say, like note to supervisor, and you can say whatever you need to say to the supervisor, that you never want him to hear because he's not going to read it. You're never going to read it. Unless you have a really very organized supervisor, you go through all the data and check. This doesn't do anything, right? So this just returns a second. So if you set it, and this is a bit odd to sum here, is kind of that this will not, you got something bad, right? And if you now say spectra 0, sorry, let's see if this worked what we did. Spectra 0. No, to supervise. No, to supervise. Okay, maybe make a simple name, then you have less risk of doing something wrong. We have it later. Okay, so that's kind of how you could add this to the spectrum. Probably this is not the most useful application. it's just to show you that unlike some other frameworks, this is really, so you have full access to everything, which means you can destroy everything you like in your data. So you, I mean, not the MGF luckily, but the operations that you do on the spectra are not limited to operations that make sense. So you can define whatever you like because there's no limit to what is useful. You can erase peaks, you can move all MZ positions by a factor of 1.3 if you like. It doesn't make sense, but you can do this. And this is just to show you that this gives you full control of what you want to do with the data. And the reason why this is useful here is because you're not limited to matchms, you're in a full-scale programming language in Python. And I'll just give you a quick nonsense example actually, but anyway, so you could define Python scripts and change all these things for you. For example, for people that are not familiar with Python, you can create loops where you iterate through elements very quickly. You can say for S in spectra with a double and then you for S in spectra, if you click return, not shift return, but only return, you see that it will not go back to the first element, but it will stop there, which is the logic of Python. So it has code blocks by indentation. And then you can go through all spectra and do something to the spectra. Let's, for example, you want to make a nonsensical, mostly nonsensical example, but it's more to give you an idea of what you could come up with. If you have the idea that you want to do something with all your spectrum data, which is not provided by any other functionality yet, or any other module, you can build your own filter functions. You can build your own similarity functions. Say you want to add a comment depending on the quality or the number of the peaks. So you could say if the length of the peaks, right, if you have a certain length of peaks, and I do this with an if len in brackets the number of the peaks part is bigger than 10, then you should do something. Right? So this situation, it cannot be a simple, it doesn't have to be a simple operation, it can be a very, I don't know, maybe you have a super custom case where you need to do something, but only if certain cases come together. Let's say you want to add a comment here. So then we can say as set, and then we make an unqualified comment, which is what I do because I'm unqualified for commenting on spectra. Like an unqualified comment, and the unqualified comment is, do you like the comment here? Nice, it has 10 peaks. That's great. Because I like 10 peaks because it means there's some data in there. And if you click on return again, and then go with backspace, you can say, okay, but we're not done yet, right? So we need more. If we say the peaks are, I don't know, maybe the next case we want to cover is, okay, it doesn't have, so this is for the non-programming people, right? So if it doesn't go in here, it means it doesn't have more than 10 peaks. And maybe it goes in here because it has maybe still doesn't have 10 peaks, but at least somewhere between 5 to 10 peaks. And then we say, okay, I just copy, because I get lazy, I copy this line. And I enter it here. And then we say, well, we'll do. It doesn't matter what you see, right, of course. The idea is more that the structure of this account is. And then finally, we have some else. So this is, we have to that. I copy this again. And then it's not going to work. Proper grammar is important here. Really like. So this is this piece of code would go through every section in our data, and it would check how many peaks does it have, and if it has a certain number of peaks, it would add different kind of comments to the data. And obviously, that's probably not something that's going to help you a lot in your PhD, but maybe from this you can abstract a bit and say like, okay, yeah, maybe there was this case when you wanted to have spectra that have instrument type orbitrap. And then they needed to have at least 12 peaks and a precursor mass of between 400 and 800. This you can build the same way, right? So the logic is the same. So you can, whatever you come up with as a selection criteria, you could program this way. And the good thing about programming is that there is no restrictions on what you can do or not, because it's not like, okay, this is not supported by Excel or this is not supported by this and that tool. Usually you can come up with much more complex use cases. And of course, if you have standard operations that are already provided, so I should say this here maybe, is if you have something that's already provided in an established software like MZ9 or somewhere else, the reason for using matchms is not to redo everything yourself, right? So this is not going to help you out. On the contrary, it's more if you have cases that are not covered by these softwares. Let's see if this works. Often not in the first case, you see, that's good. I'll check if it actually worked. So if I now ran this and it ran without error, then I expect that it did work. Also, this is not what I wanted. I want to look at the metadata. And then the metadata changed, and now we have an unqualified comment that says will do. Because we knew from the exercise before that it has 6 peaks, right? So in this case, it added the comment will do. And then of course you should add a lot of these comments in an automated way and export it as an MGF for your collaborators to be annoyed about the data. That's something to make a lot of friends. So seriously, I mean, this is really meant just as an introduction to say, like, okay, whatever you come up with as logic to add a filter or do with the spectrum, you can do this way. As I said, as I said before, there is a solution notebook also provided on the data. So if you don't get everything to run, if you have some syntax errors in here because you, I don't know, you have 2 spaces too much or something that's totally, if this block doesn't work, it's quite easy to break Python code if you don't know what's really important. Because if you, for example, add an empty space here and you execute it, and you will get some syntax errors. Oh no, in this case, it will code up doesn't care. It's not good, but okay. But you can add plenty of errors here, and don't worry if it doesn't work. That's simply because I guess we're not used to Python. The rest is kind of there's many other things that you can do with Python. For example, Python has a lot of libraries for data handling, data analysis, data visualization. For example, this is an example piece of code. If you execute this, you can just run this, and this will should produce this plot. You can try to execute this. So what this does is it's creating a plot, and most of the code is actually just for visualization. The only interesting piece data-wise is this one. So you collected all the number of peaks. Okay, I'm going to do that. This is just a Python logic of how you can go through all spectra and say, please give me the length of the number of spectra. And then you plot a histogram, and then you know, okay, oh, we have most of the spectra with few peaks. But these kind of, this is just a good example, but there's plenty of these things that you can do if you want to do data analysis. There's many ways how you can access, plot, visualize, and change data in Python. The next thing we're going to do is we're going to process our spectra. So as I said before, depending on what the data is you have, you might want to process it for different reasons. So you might want to clean up the metadata, for example. Or you might want to change something about the peaks, or you might want to normalize the intensities. Anything that you like to do, you can do the following step. And this is explained here. So in matchms, we provide already a lot of predefined filter functions. As I just showed you, you could also always write your own filter function on top of this. But for many of the standard cases, at least the ones that we know about, we already have these functions included. Which, by the way, if you realize that in your community where you work, you need certain specific peak filters or specific metadata filters, and you don't find them in matchms, then of course you can write them yourself, which we encourage. But you can also let us know, because we can only know about missing things like people tell us about, right? Because we sit in a certain corner of this huge space of metabolomics, and many things we absolutely have no idea what you guys need. So if you say, okay, it's nice, but really missing this one standard filter that's common in my research domain, please let us know. You can let us know by mail or on GitHub, and then it might be the next filter to add. And so, but so far we have standard filters that do a lot of things, and this piece of code is something I will provide. I will just briefly explain, because you can always go back into the documentation if you really want to work with it more extensively. The filtering process is done with the element I've mentioned in the slide, the spectrum processor. And you can do multiple things. So we have already default settings like basic or default or this annotated. So it's different kind of filter strengths. And what these filters do is most of the time they focus on the metadata information, because what we realize is, and that might not be that might apply to all of you, but when we work with, for example, data from public databases like GPS, it's very, let's say, diverse in terms of quality metadata annotation, and there's many inconsistencies. So a lot of the filters that we automatically run in this basic thing are just to make sure that for the 5 different names that people use for a certain field, we take them together and put them into one field. And so that some call it iron mode, and some call it iron space mode, iron dash mode, and so there's different writing styles, and we take care of it, it ends up in the same field. And we do some other checks. But you can also, there's many other filters that you can look up on the website, on the documentation. And what we do here, for example, just as an example, is we would do a basic filtering, which would just harmonize some of these metadata things. And we will then normalize intensities. That means kind of we normalize to the maximum peak height. And then we will do 2 other things. We want to select peaks, and we will only allow peaks between a certain NZ from and NZ to value. So let's say we want to, so the exercises, I think like we should enter, we should get spectral data, some in the end between 10 and 1000 Dalton. And then we do a secondary filter step, and let's say we have a require filter, and require means it will kind of throw out spectra that don't fulfill this requirement. In this case, we require a minimum number of peaks. And the minimum number of peaks, why should we do this? Here I'm doing this because later on we will use tools that depend on the peak information, because we use a machine learning model in a bit, and this is trained on data that has a certain number of peaks usually. So if you have spectrum with 1 peak, you learned in the days before, you can still learn something about it, but our tool actually is not really good enough, because 1 peak is not enough to really make a hypothesis. So we just set this number to 0. So what you have to do, you cannot execute this code so yet. You have to fill in all these common pieces. So you have everywhere where it says add your own code here, you need to add the numbers that are required. So I think it is, yeah. So what we want to have is described here. So now please add wherever you see add your code here, that's not even code so much, but add the numbers that you need. So replace these pieces by the numbers that you think are appropriate, and then you can run this code cell. Yes. So what is the minimum number of peaks that we accept? So let's say everything that has less than a minimum number of peaks we're going to throw away. So now this is really now the fragments that we just saw of. So every peak has a number of these network fragments, right? We have 2 or 3 fragments, 5 fragments, yeah. And this is really, so yeah, sorry, peak is maybe not like for being accurate. It should be fragmented, yeah. You can replace it if you prefer just like fragments in there, that's fine too. Then you have to replace it. But that's what I meant. So you have to, in your spectrum, you want to reduce it to a certain number of fragments. Yes. Yeah. Yeah. Oh yeah, sorry, that's confusing. So this is what it's if I don't specify anything else, it will automatically specify that. So you don't have to do anything like this. Yeah, then you could change it in here. So there are ways to kind of set the maximum for but I think I have to look at it. I think we don't really account for this yet. So you can do this manually, but this would be something that, I mean, if you want to set it to 2, I think that's probably not a common use case, but then you could do it yourself. Yeah. Yeah, you could do the max function. Then I mean, ideally in Python, that's a thing. If you're one of the few people that want to have a value of 2 as a max, then you can run this filter, and then later on you add something like a loop, as I described before, and say, okay, multiply by 2. So I guess you figured out that the numbers are exactly just copying the numbers from you, right? So you can take the minimum number of peaks 4, and you can say here from where to where you want your 20, choose 10. And if you run this, how many spectra are left? Somebody get a number from this.
3,802.
Okay, that sounds about right, I think. So what you see is now that this is taking a bit of time. Because it will run, essentially, I mean, it's not only the stuff that you edit here, but in the base, there's a lot of filters that run for every individual spectrum. So you see that it's processing these 6,100 something spectra. And once you're done with it, it will execute this part where it says how many spectra are left. And actually, I think we should get something that is about the number. That,
All the way to the right.
oh, it's here. Okay, sorry. Yeah. That's not very clever, but it's in the end of it. So number of remaining spectra is 3,802. You should get this number. It's not super critical if you don't, but if you put the same values in there, you should get the same number of spectra left. So it means we just removed quite a bit of our data. This is a meaningful step for us because for the tools like SpectraDeck and Institut score, we need these peaks. We need a certain number of peaks to get these data. If you just, this is maybe you have to do nothing, it's just to inspect and show you what happened. So this was the plot that we had before. And this means we had a lot of spectra with a few peaks, and now we don't have it anymore, right? So we just removed everything that is below 4. So in our data now, there is no spectra with less than 4 peaks anymore. It's just as a control. And it means that we now have to work with spectra clean, or if we want to, we have to work with spectra clean. And the metadata looks slightly different. It's not a lot of things to add, because this is what I added here. You don't might have it, but this is what we have here. Yes? Perfect. Yes, but it's a bit hidden now. So we added this spectrum processor that we have now on Friday. So but this is actually what others are now working on. So to get the information of, so because now if we can export the workflow, and then it will say which filters were run with which parameters in which order. But ideally, of course, we want to get it if it's like we want to have like a help or print function where we can get the information as well. Because now you find it, but you have to go into the code, which is not what we like to have. So it's in there, and it will be exported as a YAML file, but it's a bit hidden, or still, I think the next release will have this. Yeah, so actually the things that we did is we are a bit in a trade-off situation that we don't know exactly what kind of user groups are using the tool. And so these default and basic settings are just to make it easy to use, but of course they hide a bit of information. So it's a bit of trade-off. Ideally, in the past, what we've done, we really collected all the filter functions and put them in a script. But it turns out that this is not so easy because some of the filters need to be run in a certain order because, I don't know, you have to add the adduct information first before you do something with the adduct. So if people would use the filters and just execute them in the wrong order, they would get weird results. So this is something we now try to prevent, that we streamline this a bit better for users. Okay, so this is about what we have now. As a final example for this matchms part is, I'd like to do one thing before the break. I hope we can get it done first. This is very quick. So if you have spectrum, it's not, I mean, you don't expect matchms to be a spectrum visualization tool, right? So this is not its main purpose, but it has some functions to plot your spectra. And I think this is a very ugly one. You can take any other number. One is good, okay. Let's say one. So they have a plotting function. And this is not meant to be the fanciest plot in the world. It's more for you to give some kind of information about what your spectra look like. And if you execute the other codes, you can maybe also you change the number, some prettier spectra. Whatever spectra you want to plot against another, you can get these mirror plots where you compare two spectra, and you can see we're going to use the linear default. So this is how you can kind of match, or not match, but how you can compare two spectra. And this is a part with the range. So there's multiple plotting options, but that's about it, what you can do with plotting. So there's no interactive spectrum plot, there's no fancy other thing. This is what you should do elsewhere, right? So if you really want to have nice and fancy spectrum plots, this is not what you're going to find here. This is more for data inspect. So if you work with spectra and you need to know what's happening, something weird, it is good enough, but that's actually it. We're coming to the core piece of, so now we're done with the processing. We have reduced our number of spectra, we have done some things to them. And actually what we often want to do in matchms is kind of really to compute the similarities. And the similarities are calculated in such a way that you have this kind of script, right? And you can pick any spectrum similarity that's provided in matchms. There's a couple of them, some are listed here. Now we are going to use precursor mass match and we use a cosine score. It's called cosine greedy because there are different algorithms for cosine. And these are the two we're going to use here. We have several more in matchms, and there are several ones that are in external libraries like Spectrac or Institut score. But here we start with them. The only thing is to do is you should set some parameters. So there's actually only one real parameter that you should set here. Pick a tolerance. The tolerance means kind of what do you accept as a precursor answer difference. And of course, the smaller you pick the value, the less matches you will get. But whatever your number you pick, that's up to you. So you can set any value you like. We could start with a tolerance of 0.1 or something like that, right? So that's not great, but you could do, depending on what your instrument type is, what your data quality is, you can choose different parameters here. But let's start with 0.1. And this will mean that it is now it's comparing all spectra, all of the 3,800 spectra with each other, and it's just comparing, it's just giving you a 1 when it says, okay, this is within this window of precursor enzyme. We can run this. This should be fairly quick because actually it's not a very complicated computation. So it really just is comparing the precursor matches here. But what do we get? And okay, this is just to ask you, what would this number stand for? 3,802 squared. So 3,802 times 3,802. What number? Okay. Yeah, 3,802 is the number of spectra. And if you square it, so this will be the number of possible combinations. Right? So spectrum 1 with spectrum 2, spectrum 1 with spectrum 3, and so on. And you would get an array of 14 million simulations. That's still handleable, but of course most of that will be 0, I can tell you, because with this thing here, it means most spectra are not within the reach of the other spectrum. So what you get instead is you can look at, if you have this scores element, and you can type scores.scores, and you'll get some information. So what we actually have, what this actually computed is, I mean, it compared all spectra, but it didn't store them. It stored only the ones that are interesting, and these are the ones that are a match. So instead of storing 14 million information, which are usually 0, we only stored the ones, I think 43,000 or something. The rest is, of course, you can, like, I mean, of course, here it's easy to guess what they are, but we don't need to store them. So that's now so why I do this is kind of because other computations might not be as fast as this one. For example, if you compute the cosine score or other things, they can take a while, or if you have your own custom scores, they can be very slow, depending on what you actually want to do. So sometimes having such a step as a first step is good because you already nail down the interesting pairs to a much, much smaller number. So what we can do next is we can apply another score. So for this, I think it's not prepared, so we have to type it. Yes. So we define another, for example, how we call it is up to you. So I call it cosine similarity. And this is the cosine gradient that we import before. This will also be a parameter. It doesn't need to have a parameter, but you want to give it a parameter. The tolerance. And sometimes you get this help information if you like it. But the tolerance is exactly the same. So what is a match? And depending on your resolution and on whatever you want to find, you can set a tolerance. Let's go for 0.01. You can really make it 0, or it doesn't really matter here. We'll change the result here, of course. So we set, this is another score that we want to compute. By this, we define what we want. So this is, we say we want this cosine score with these parameters, but it's not computed yet, right? So this is not how it's computed. But we can do the next set is scores.calculate. I'm always happy for the help function and then get it. Calculate, there it is. Calculate. And then we add this cosine score. Cosine similarity. Similarity. This should actually do it. So with it, we are calculating all the cosine scores. And this is not all the cosine scores between all pairs of spectra, but only between the ones that we have a precursor match for. Otherwise, it would take much longer. And then if we look at scores.scores, we should see something different. So now we still have the same number of stored elements. We didn't remove anything yet. But we have more scores stored. So we have a precursor mass match, we have a cosine score, and we have also cosine matches. This is kind of the number of peaks that actually match. So there's now 3 pieces of information that we can take together. And yes, so this is what I think in view of time, I would like to skip the next part so that we can move on to understanding the score. But this is about what you can do. And then if you have these scores computed, then so we will, I will have this. So the inspect results are here. You can just execute this if you want. It's already prepared. You can look at the results, and what you can see that is kind of okay for a certain spectrum. For example, spectra claims 2. You can add any number you want. You get these results. So you get okay, this is the spectrum itself, but then you get the nearest other pieces, and we found one other spectrum with a cosine score of 0.98 and one with 0.88, and this is the number of matching peaks. And if you have this information, then depending on what your aim is, you could probably add a threshold, because, for example, here we see that there's a lot of low scores, which is really not that interesting. But that's up to you of what you want to remove and what you want to keep. So the rest of the code cells are in principle done, so you can, I think we will skip it for now. So what you can do in principle as next steps with matchms is kind of you could filter them, you could remove spectra, and then you can eventually, if you like, you could create a graph out of this. So you could say like, okay, if you have a threshold, just create a graph for every spectra that are connected by a certain score. So this would then be back to molecular networking. You would get a graph in all file, which you could then load again into Statens. But I'd like to stop here. Unless there's a question on this part now, we're going to see a lot of this code again in the next notebook. Yes.
Steps before we run again the scores, right?
Yeah, the scores is not executing anything, it's just to inspect.
Okay, so what do we need to see?
Yeah, it just tells you what's in there. So what it has stored, okay? And what it has stored is it says it has scores containing for these 3 different kind of scores. So you can stack many scores on top of each other if you like. And so this is to know what's in there, because you sometimes have to refer them by their name later.
Okay, and the number number didn't change, so
The number, because in the first step, we removed a lot of potential pairs because they had no precursor mass match and that match. So they were removed, right? Because they were zeros. And so we stick with them. But actually, a cosine score you will get for any of these elements. In some cases, what you see is what you see here. It might even be a cosine score of 0. But it's still, you can see that all of them have a score of 1 here, which is the precursor MZ match. So all of them have a precursor match. So all of them are within 0.0 Dalton of precursor MZ to the original spectrum. And these are the cosine scores that we found for them. And these are the number of matching peaks.
so in this case, even if we lower the tolerance, then nothing will happen.
So if you lower the tolerance, you will affect these numbers here. So the scores will change. Because what is considered a matching peak will depend on the tolerance. So if you change the tolerance, if you increase it, you will get more scores that have high scores by accident because they have peaks that is similar but not identical position. And the same way around, if you lower the tolerance, you will get tendency towards lower scores. And then there's what we didn't do. You can remove. So you could say like, okay, now you want to again reduce the amount of data, and you want to say like, please remove everything with a cosine score below 0.7 or something. Then you can remove this too. Okay, so I think we can do a break in a bit, but before the break, just that we have something to do for those that do not get it to run, is we start a second method where we are going to repeat a bit of this, but that's pre-prepared. And we're going to work with a deep learning scoring methods and the deep score. And this is the other notebook that is called, I put it up, but it's called.
Should everyone go to the new notebook?
Yeah, so you can save these, export this, close this, whatever you like to do. We're not going to use this again now. It's called Summer School and Institut Deep Score. Live coding and actually roughly here. And the goal is that we can start going to the break, but we can already execute the first piece so that it already installs all the dependencies. What you see here is we're not going to install matchms. We are going to install Institut Deep Score. But this will automatically install matchms because it requires matchms. That's a longer type. This is also called live coding at the end. This is in the same. It should be in the same folder of the Dry folder. And it's called somewhere is NSTD folder. And since we are going to use after the break deep learning models, it has to download much more libraries. So that's why it's good to start it before the break. It won't take too long, but I think it's a good thing to fix in the break. If you have trouble running this notebook, running it, just,
If everything is as it's supposed to be, so
Yeah, yeah. And if you go back to the first week, it will already install the.
Yeah, it's the same message as the last one. I was pretty you were running it on your own computer. Yeah. So it was going to be different. You have to get much worse. What did you decide that you were doing your own?
I'm trying to get used to this.